Lighthouse Scientific Education presents a lecture in the Atomic Structure series. The topic is Discovery, Parts of the Atom. Material in this lecture relies on understanding of the previous lecture, Order in Matter. It is helpful to review some of the history that leads to our modern understanding of the atom. We will begin in ancient Greece with some early thought on matter. Before we begin our journey into the discovery of subatomic particles, we will give ourselves a heads up with a brief review of the current understanding of the atom. Our first stop on the road to discovery is radioactivity, specifically alpha and beta particles and gamma rays. Then it's on to the electron, using the cathode ray and arriving at Millikan's oil drop experiment. Next to the proton, with a stop at the Plum Pudding Model and Rutherford's gold foil experiment, and finally, elucidation of the neutron. The beginning. In ancient Greece, philosophers pondered the question, can matter be broken down indefinitely, or is there some smallest bit of matter? For example, if one takes a bar of pure gold and breaks it into half, there'll be 2 pieces of gold. Take one of those pieces and break it in half. That produces 2 even smaller pieces of gold. Say that there was a machine that could keep breaking apart smaller and smaller pieces. Could this process be done forever? Or is there a physical limit such that breaking some tiny piece in half no longer yields a smaller piece of gold? A group calling themselves the atomists believed that there was a smallest uncuttable bit of matter. Considering that there was no way to explore this concept experimentally in ancient Greece, is a pretty impressive thought. Another thought proposed by one of its prominent members, Democritus, was that each type of matter was composed by its own type of atom. And there is some truth to that. Still, it took 2,000 years from Democritus's time before Dalton would propose the first modern concept of the atom, and that is covered in the Order in Matter lecture. Let's take a look at the modern atom and familiarize ourselves with its basic components before we discuss their discovery. The modern atom is composed of 3 subatomic particles: the negatively charged electron, the positively charged proton, and the neutral neutron. The history of the modern atom involves the discovery of the subatomic particles, revealing their 2 main properties, mass and charge. Remember that positive and negative charges attract, positive and positive charges repel, and negative charges repel. The exact nature of charge is beyond the scope of this course. The same could be said of the exact nature of gravity when studying physics. In both cases, knowing the exact nature is not required to apply their properties. And then there is the discovery of orientation or location of the subatomic particle in the atom. For the discovery of a subatomic particle, there needs to be a breakdown of the atom, and that is radioactivity. Radioactivity was discovered in 1896 by Henri Becquerel. He showed that a piece of uranium emitted energetic fragments that could expose a photographic plate through black paper and even over a short distance. The atom of uranium was breaking or splitting and was therefore made of parts. Ernest Rutherford, a name that comes up frequently in the early study of the atom, applied an electric field across the radioactivity path. 2 metal plates attached to a power source generates an electric field. Since this whole charge business might be a bit confusing, let's familiarize ourselves with the electric field. The metal plate attached to the positive terminal of the power source is called the anode. The anode attracts negatively charged particles. The anode repels positively charged particles. The metal plate attached to the negative terminal of the power source is called the cathode. The cathode attracts positively charged particles. The cathode repels negatively charged particles. Rutherford found that radioactivity came in more than one form. There are negatively charged beta particles that are attracted to the positively charged anode. That is, that they were bent toward the anode. As a heads up, these particles are actually electrons. Then there are the positively charged alpha particles that are attracted to the negatively charged cathode. These high energy particles would later be used in defining the proton and the nucleus. Another form of radioactivity did not have a charge, so was not bent by the electric field, and would be discovered later. Paul Voulard would come to identify that form as the gamma ray. This form of radiation is actually a kind of very high energy light. And while we will not get into it, Pierre and Marie Curie would add significantly to the study of radioactivity. On to the discovery of the electron. We should be familiar with the electron. Electricity is moving electrons. J.J. Thompson and others would use an evacuated tube, that's no air, containing electrodes, a metal plate anode, and cathode at each end to generate a ray. The ray is a beam of electrons. They come from atoms in the metal of the cathode. They are attracted to the anode since the anode attracts negative particles. Thompson concluded that electrons were negatively charged. The letter Q is used to designate a charge. The negative Q is therefore a negative charge. Applying a magnetic field across the beam caused the ray to bend. This too might be familiar. It is how the old-fashioned picture tubes work. So, electrons have a charge, Q. How big is it? Well, electron charge is 1.60 times 10 to the negative 19th coulombs, where the coulomb is a unit of charge, and 10 to the negative 19th is really, really small. Where did that value come from? In 1909, Robert Millikan and others performed the famous oil drop experiment. That's where he suspended oil drops in an electric field. We will cover the experiment with enough detail to get an overview, but not enough to get caught up in the math. Drops of oil were produced in the upper chamber of the device. They used an apparatus like an old-fashioned perfume bottle with a squeeze bulb to generate drops. Some of the drops fell through the hole in the upper electrode, the positively charged anode. Those drops that fell through were exposed to X-rays, causing the formation of electrons on the drops. And yes, they knew electrons were negatively charged. Some of the drops became suspended between the electrodes. Drops were suspended between the electrodes when the force pulling up on the electron filled drops, that's the attraction to the positive anode, which is the charge of the electron times the electric field, was equal to the force pulling down on the drops, and that was the mass of the drop times gravity, or its weight. Millikan and his co-workers were able to deduce what the charge Q on the electrode must be to keep the drops suspended, and that was 1.6 times 10 to the negative 19th coulombs. Again, we're not concentrating on the math, just the results. During Millikan's era, that's the early 20th century, there were a number of prototype models of the atom. While the atom hadn't been completely explained, there were important understandings already made. From radioactive experiments, it was known that the atom contained particles of positive and negative charge, the negative being electrons. J.J. Thompson proposed an early prototype of the atom referred to as the Plum Pudding Model. The model held that the atom was spherical. It had a median or a sea of positive charge. That's the pudding, colored gray here. Small bits of negative charge were embedded in the atom. That's the plums, colored orange here. This model leads us to our next subatomic particle, the proton. In 1909, Ernest Rutherford and Hans Geiger set to test the Plum Pudding Model. They generated and shot a beam of high-energy positively charged alpha particles at gold foil. A ring capable of detecting alpha particles surrounded the foil. They expected most of the alpha particles to pass straight through. Some particles would be slightly deflected by the positive C and the negative plums. Rutherford considered it like shooting a cannonball at tissue paper. We can use this cartoon to explain Rutherford's expectation. Imagine this row of plum pudding atoms as a sheet of gold foil. In reality, foil is millions of atoms thick. A high-energy positively charged alpha particle is shot at the foil. It enters the atom, is barely repelled by the sea of dilute positive charge, and doesn't strike one of the negatively charged plums. It goes through unaltered, maybe slowed down a bit. Another particle is shot at the foil. It bumps into a negatively charged plum and is slightly deflected. This goes on, with many going straight through and a few slightly deflected. That is what they expected. What did they find? They found that most of the alpha particles did pass straight through, but others deflected more strongly, and some even bounced back. The Plum Pudding model could not make sense of this, so they thought that if a model with the atom as a sea of positive charge with small bits of embedded negative charge didn't work, what would? Well, what if in the atom much of the mass and all the positive charge is in a small area at the center, a nucleus, and that outside of the nucleus there is a sea of negative charge? Now the negative charge is the pudding and the positive charge is concentrated as the plum. That is the exact opposite of the Plum Pudding model. A couple things to note here. The nucleus is drawn in this cartoon atom much larger than it really is. In reality, if an atom were this size, the nucleus would be microscopic. And then there is the sea of negative charge as the pudding. By Rutherford's time, the electron was known to be a negatively charged particle, so C is a misleading concept. Rather, it was believed that the negatively charged electrons in the atom repulsed each other, such that they were spread out about the atom. The upshot of this is that with a tiny nucleus and electrons spread out about the atom is mostly empty space. Wow! If we use this model of the atom for the gold foil, we would see that since the nucleus is so small, most of the alpha particles would at most cross into the sparsely populated sea of negative charge and pass straight through. A few alpha particles would get close to the positive nucleus and be repelled. Since the nucleus is of such concentrated positive charge, the deflection would be greater than it was expected to be in the Plum Pudding model. A very few alpha particles would have a trajectory that involved a direct impact with the atom's dense, positively charged nucleus. This would cause a positive charged alpha particle to ricochet backwards. This is not an option in the Plum Pudding model, where the positive charge was spread out about the atom. Rutherford's experiment righted the model of the atom. In 1920, Rutherford named the positively charged particle the proton. The last subatomic particle to be identified was the neutron. In the 1930s, James Chadwick and others would reveal its presence. Chadwick was a student of Rutherford's. At the time, it was known that the mass of an atom was heavier than the combined mass of the protons and electrons. There had to be another particle in the atom that has mass. Chadwick showed that the high-energy alpha particle, remember that's a form of radiation, had a neutral particle with a mass approximately the same as the mass of a proton. He called the neutral particle Neutron. And that high-energy alpha particle, well, it was really the nucleus of a helium atom. 2 protons and 2 neutrons. And so the parts of the atom were revealed. The modern atom is composed of 3 subatomic particles, negatively charged electrons, positively charged protons, and neutral neutrons. The protons and neutrons reside in the nucleus at the center of the atom. Electrons orbit the nucleus, and more on that later. To recap what we've covered, Democritus of ancient Greece believed that each type of matter was composed of its own type of atom. Radioactivity was discovered by Henri Becquerel. The Curies would make great advances in radioactivity. Ernest Rutherford applied an electric field across the radioactivity path. Electric field is generated by a power source with a negative cathode and a positive anode. That field caused the negative beta particles to be attracted to the anode and the positive alpha particles to be attracted to the cathode. Paul Voulard identified the uncharged gamma ray. J.J. Thompson used a cathode tube to generate a ray of negatively charged particles, electrons. In 1909, Robert Millikan performed the oil drop experiment, which measured the charge on an electron. He suspended oil drops and compared the upward pull to the downward pull. In the Plum Pudding Model, the atom is a sea of positive charge with bits of embedded negative charge. Rutherford and Geiger's gold foil experiment showed that much of the mass and all the positive charge is in a small space at the center, the nucleus. Outside of the nucleus is a sea of negative charge. The experiment is credited with showing that the atom is mostly empty space. Chadwick found a neutral particle with a mass approximately the same as the mass of a proton. He called the neutral particle the neutron. The modern atom, the proton and neutron, reside in the nucleus at the center of the atom, and the electrons orbit the nucleus. And that concludes our lecture on the discovery of subatomic particles. Be sure to review and connect the names of the discoverers to the subatomic particles.